We're going through a particular derivation of the Kalman filter. Um, we started this in a previous video. Here is the system model that we start with. This is kind of a given. And then we started the blue process, best linear unbiased estimation process. By the way, here is the state space model we're dealing with. It's a discrete time state space system. I won't go through all that again. We did this before. We showed that, well, here's kind of how we're going to do things. We update and estimate, and we update and estimate the time step K based on our previous estimate for time step K based on previous measurements. But now we're going to crank in a new estimate at time K, a new measurement at time K, I should say. So this is the way we sort of update our state estimate. And we said, or this whole page shows that the mean error is 0, or we're unbiased if this estimate prior to processing the measurement at time K was also unbiased. So now let's look into that. What do we do between measurements? What we did in the previous video to kind of show what happens to our estimate and the covariance of the error of our estimate as we process a measurement at time K. How did we get up to time K? Well, we need to propagate the state. We need to do two things. We need to propagate the state and we need to propagate the covariance. This chart is on how to propagate the state. Here was from the system model. Here's the state equation from the system model. Well, it makes sense if you're going to estimate this, and this W is a zero mean random vector, that you would just make your estimate this v sub k times your previous estimate. You know, as you go from k to k plus 1, you take your estimate at time k, multiply it by this phi, and that's what you expect the state to be at time k plus 1 before you get the measurement at time k plus 1. Well, let's see if that's unbiased. If this estimate was unbiased. Actually, I left this for homework for my students, so I'm going to zip through this here too. You can follow this. I'll just hopefully, I don't want to go through it step by step. Here is the error then, what we estimate versus reality. And plugging in what they are, we get the terms, we'll take the expectation, and if this error was 0, we're going to get a 0. And this was the error we had before, which was what happens after you process a measurement. It said it was unbiased if this guy was unbiased. And now we can say this guy's unbiased if this guy's unbiased. So we stay unbiased. When we propagate to the next time step, we're unbiased if we started unbiased. So we always remain unbiased if our very original estimate was unbiased. So we've imposed the unbiasedness, and here is the way we're going to propagate the state. What about propagating the covariance? Here's what we mean. And actually, this should have a little superscript on it. Here's what the covariance we're looking for is. It's the covariance at time step k plus 1 prior to processing the measurement at time k. It's by definition what it is. Then we just plug in the terms and do all the matrix arithmetic. Again, I assign this for my students for homework because I didn't want to do all the matrix stuff myself. I wanted them to at least do a little bit of matrix arithmetic. And anyway, you get this as a way to propagate the covariance matrix. And we know all this stuff. So where does this filter stand? We have our propagation equations, which take us from time step k to time step k plus 1. But these are after processing the measurement at time step k, and these are prior to processing the measurement at time k plus 1. That's what superscript means. Then we have the so-called update or correction equations. Here's how we update the state time k given the measurement at time k. It's based on previous state estimate, or it's based on the estimate at time k, but before we process this measurement. And now it is, here's what it is after processing. It's kind of hard for students to grasp the first time they see this. And then we had this equation from the previous video of what the covariance of the error of our estimate is. The error in this estimate, it was this, regardless of what we choose for this gain k. So we've done the LUE of blue. All that remains is find the best. Still need to find the optimal gain. And we're going to do that by minimizing the trace of this covariance matrix. Right. Why does that work? So let me talk about what do we mean by best. We mean mean square error, minimum mean square error. This is what mean square error is. I'm going to say it means this. Like I kind of went through this quickly in previous videos, so let me go through an example so you can see what's going on. Our state, we'll say it has 3 state variables. Our state is a vector of 3 variables, x1, x2, x3. So x hats of 1 is our estimate of variable 1. The error, this tilde, in that x plus 1 is just estimate of 1 minus the true of 1. So this error vector is these 3x tildes. The transpose of that error vector is this row vector. So we have a column vector and a row vector. If I do this row vector times that column vector, here's what I've got. And if I take the expectation of that, I've got this expectation. Well, what is this? Do that little matrix multiply. We just get these 3 expectations. That's the sum of the individual mean squares. That's the thing we're minimizing. We're actually minimizing the sum of the mean squares here. Now let's look at this guy, which looks similar to this guy, but we reverse the order of the transpose. So now this guy is a column vector times a row vector. You get a matrix out of that. And what is the trace of this guy? It's the sum of the main diagonals, which is this same thing. So if I minimize this guy, I'm minimizing this guy. And I'm also minimizing the trace of this guy. They're all the same thing. Why do we want to mess with this thing? Because we have tools, sort of matrix calculus tools, of how to take the derivative of a trace. And we're going to take that on faith. So I'll save this for another video, but here's all the math behind the trace. I'll just save this for another video because I don't want to rush. Sorry this takes so long just to derive the darn thing.